All right. First, there's a property of proportions that we didn't talk about yesterday or the day before. Can't remember. That I want to cover yesterday. I guess I want to cover. Notice this. Now, if we start with a ratio equation, consider this to be some algebra that we can do, some algebra steps. We're going to be setting up ratio equations a lot. That's what this chapter ends up being almost exclusively about, is recognizing ratios and setting up equations for those ratios. So here's the first property I want to talk about today. Notice that if we start with the ratio equation, A over B equals C over D, then I can exchange diagonal elements if I want to. So I can do that. The B and the C can switch, or I can switch the A and the D. Doesn't matter, either way. So if I switch the B and the C, then the C ends up being on the bottom of the first fraction, and the B ends up being in the numerator of the second fraction. That's okay to do. That's convenient sometimes. For example, if we were solving for x, let's say I had the fraction 2 over x equals 7 over 3, something like that, and I want to solve for x, I could cross multiply. That's fine. It would work. The other thing I could do is I could exchange diagonally and get 2 over 7 equals x over 3. And then what would I do to solve for x there? How do I undo dividing by 3? Multiply by 3. I could multiply each side by 3 over 1, and the 3's would cancel, and I would get x equals, if I multiply straight across, 3 times 2 is 6, over 1 times 7. Okay? So that's a question.
Let's say on my assignment, it was kind of like the one on the bottom right thing. It was like m over n equals 14
over 9. Yeah, let's look at one like that. Good. Okay, so the other property is this one on the bottom here. Okay, this is kind of a weird one. Now watch this closely. What this is saying is, if we have a ratio equation, I can add the denominators of both sides into their respective numerators. So I could say, I could add this b into the quantity on top. So it could become a plus b all over b equals c plus d all over d. Right, like this. And the reason we can do that is, now watch what happens if I split these fractions up into 2 fractions on the left and 2 on the right. If I break up the common denominators into 2 separate fractions, I get a over b plus b over b equals c over d plus d over d. Okay, does that make sense? Well, yeah, it does. What's b over b? What's b divided by b? 1. What's d divided by d? 1. So all I've really done is I've just added 1 to both sides of an equation. That's okay to do, isn't it? Right? Okay, so that's another property that works. So in those problems on the... So let's try one of those. Let's try one of those. So what if we had, like, say we had a over b equals 3 over 7. I want to know what over b equals 10/7. What did I do to the right side of that equation? I must do the same thing to the left.
Good. Why do you want 10/7?
So it'd be a plus b equals...
Ah, good. So look what I did. If I add 7 into the numerator, that gives me 10.
Okay.
Right? So on the other side, I have to do the same thing. I've got to add the b into the numerator and get that. Right? Now in Moodle, how would I enter that whole thing? Well, I'd enter it as, I think they say something like 10/7 equals what? So your answer would be the quantity a plus b divided by b. Okay? All right. Okay, so I think that's all we need to do from that one. Okay, so I want to take a quick look at 8.3, similar polygons. All right, now look at the criteria here, please, for what it means to be similar. When there is a correspondence between two polygons such that their corresponding angles are congruent and the lengths of corresponding sides are proportional, then I say the two polygons are similar. Okay? And the way we talk about similar polygons is we're just going to, just like we did with congruence, we're just going to write the vertices of the polygons in corresponding order, right? So in this case, vertices A, B, C, and D would correspond to vertices E, F, G, and H. They go together. So there's a precise order that we'd have to state those in. Now I want you to notice the symbol that we use. Look at that symbol. It's a tilde. Where have we seen that tilde before?
Above equal signs.
Okay, in a congruent symbol, right? Now think of the congruent symbol as having two parts to it. The congruent symbol had the tilde on top, and it had the equals on the bottom. Okay, what did we say were the criteria for congruence? Same. What? Two objects are congruent if they have the same. Well, true, but just in general, same size and shape, right? So we could think of these two parts of the congruent symbol as representing those two things. The same shape part is going to be the tilde part, and the same size part is the equal sign. Right? It's helpful to think about it that way. Because equal makes sense, because all the measures of all the sides and angles would have to be equal, right? Now, congruence is just like similarity, except similarity is a little less specific, right? With similarity, we're just only requiring the same shape, but not the same size. So we're just going to erase that second criterion, and we just get similarity. How about that? Okay. Okay, so here's an example of two similar polygons. A, B, C, D is similar to E, F, G, H. And look, this shows all that stuff. All the corresponding angles are congruent, right? Angle C is congruent to angle G, angle D is congruent to angle H, etc. And it tells us down here that the corresponding sides are all proportional. The ratio of the length of AB to the length of EF is the same as the ratio of the length of BC to FG, which is also the same as the length of CD to GH, etc. Right? See how that works? So we get this whole series of ratio equations. Thank you. So then, I don't want to do the whole thing here, but let's just pick a couple. List all pairs of congruent angles. Well, let's not list them all. Just list some. What's somebody give me an example of a pair of congruent angles here?
JKL, ST.
Okay, angle JKL, which maybe we could even just call angle K here, is congruent to angle T. What's one more? Okay. Okay, so okay, in other words, not K and S, you mean J and S. There we go. Okay, one more. N and W. There we go. We're getting the idea. Right? Okay, now how about size? Give me a proportion here. I want to know, give me a ratio equation that's showing proportionality between two sides. So what's one ratio of proportional sides? Here, get us started.
ST over, or is to JK.
Okay, so ST over JK would express the proportionality between these two figures, right? The ratio of ST over JK would have to equal what? Somebody give me one other fraction that would have to be equal to that. One other ratio.
TU.
Okay.
KL.
TU over KL. Sure. Another one. Somebody else. What's another one? Okay, WV to NM. Okay. Okay, everybody see that? Because those two would go together. What else? Yeah, answer me this. What if, I'm going to suggest one. Could I say, well, let's see. Those two sides go together. So could I do JN over SW? Seems like I'm playing the same game you guys are. Is that right? Yeah, I did it backwards, didn't I? Right? Because notice that in all of these ratios you gave me, I've had the small lengths on the top and the large lengths on the bottom. So I have to continue with that. What I did was wrong. Right? It should be SW over JN instead. Right? See that? Good. All right. Okay, so now I want you to decide for me. Are these two sides, or are these two figures proportional? Okay. How come they're proportional? They're similar, I should say. Say it again. Okay, that's true. What about the sides? Yes, sir.
They're all proportional.
Okay.
Corresponding sides.
They're proportional. If we look at corresponding sides, they are proportional, aren't they? Let's look at the ratio of. There's two corresponding sides. So, whoops. So 6 over 4. What's another ratio of corresponding sides then? Big to small. 9 over 6. What's another one? And the last? Are those all the same?
No.
What are those all reduced to? 3 over 2, sure. Okay, so 3 over 2 is the important number then. That's the number that relates these two similar figures, right? That's what we call, by the way, the scale factor. Is that fraction? Because it tells us how many times bigger is the big one, right? 1.5 times bigger, 3/2. Okay, so what about this? You see a bunch of problems like this. You've been asked to create a poster to advertise a field trip to see the Liberty Bell. You have a 3.5 by 5 inch photo to go from here, and you want to enlarge that. You want the enlargement to be 16 inches wide. How long should it be? So the short dimension would be 16. How would I set this up? Okay, that's one way we could do it, sure. We could do that. We could say 16. Oops. Okay, we could say 16 over 3.5 equals what? What are we looking for? X, you said, right? X would be the unknown. So X over 5. That makes sense, doesn't it? Right? The ratio of the the full size or the enlarged width to the original width must equal the enlarged length to the original length, right? Corresponding sides. And then I just solve for x. How would I solve for x? I could cross multiply. I don't actually have to here though, because all I have to do, solving for x means isolating x. I just have to get it by itself. Multiply by 5, sure, because right now x is being divided by 5, so if I multiply both sides by 5, I just get the answer then. X equals my original ratio on the left, 16 over 3.5 times 5 over 1 times 5, right? That's my answer. So 80 over 3.5, which if I divide that out, that's going to give me 22.8 something, so about 22.9-ish. 22.9, roughly, approximately. Okay? Okay, one last thing here. One last thing. We have a rectangular patio around a pool. Okay? And the designer of this pool has done something kind of interesting here. He's wanted to make the patio similar, the rectangular patio similar to the rectangular pool, geometrically similar. He's poured this thing so that the ratios are proportional, right? Well, first of all, what is the scale factor? If the pool and the patio are similar rectangles, what's the scale factor that describes the two? So I just need to get the scale factor. I just need to find a ratio of corresponding sides, right? So what would I get? Go ahead. Okay, and you get that probably from, say, 48 over 32, for example. Okay, so the scale factor equals the length of the outer rectangle divided by the length of the inner rectangle, which reduces to just 3 over 2. Okay, the patio is 1.5 times the dimensions of the pool. Okay. Now, what about the perimeters? Let's see what happens with the perimeters. Anybody want to make a prediction here? The ratios of the perimeters, do you think they will they will be 3 over 2 or not? No? I'm hearing some no's. Okay, let's see. What is going to be the ratio of the patio if it looks like it's 24 feet by 48 feet? So 2 times 48 is 96, plus 2 times 24 is 48. 96 and 48 is what? No. 96 and 48? No? 140. Not quite. 144? Okay, would be that's the perimeter of the outer rectangle. What about the inner? Whoops. 2 times 32 would be 64, plus another 32. 64 and 32 is 64 plus 32. 96. Well, is that ratio the same? (144 over 96). Does that work out to be 3 over 2? Yeah, it does. How about that? Okay, that's pretty important. Okay, what we just said there. Now, I want everybody to listen closely to this, because this is a big deal. If we have similar figures, then all of their, not just the outer dimensions, all of their measurements, their linear measurements, are going to be proportional. Anything we could measure with a measuring tape, okay, is something that's going to, those are all going to be proportional. So the perimeters would be, if I looked at the diagonals would also be in the ratio of 3 over 2. What about the areas? Think they would be? Yeah. Let's calculate and see. 32 times 16, that's going to be 512, I think. Is that right? Yeah, I think that's right. Yeah. So 512 is going to be the area of the pool. 512. What are the units going to be for area? Square feet. Okay? The area of the outer rectangle, that's 48 times 24. Oh boy, that's a big one, huh? Let's see, what's that going to be? 50 times 20. Well, here's how we can do that. 50 times 24 would be 4,800, right? Yeah, 4,800. Is that right? 50 times 20? No, I'm sorry. 1,200. Okay. So then I'd have to subtract away. That's 50 times 24. So I got to take away 2 of those. So take away 48. So I'm going to get 1,200 minus 48 is 1,152. Okay. So the big one is 1,152 square feet. Is that ratio also 3 to 2? 1,152 over 512? No, it's not, is it? Not even close. 3 over 2 is 1.5. 1,152 over 512 is going to be about, looks like that's about 2.2-ish. It's a lot bigger. It changed. It changed, didn't it? Did I just lie earlier again? I told you earlier that the ratios of all of the linear measurements would be proportional. Now, is that a linear measurement? Is that something, can I measure area with a measuring tape? No, I can calculate it from those measurements, but I can't measure it with a measuring tape, right?
So you lied.
So I didn't lie. So I was telling you the truth. So the ratios of all the linear measurements, anything I can directly measure with a measuring tape, those would all be proportional, but area is not one of those things. So I shouldn't expect the areas to be proportional. They're not. Okay? The areas don't fall in that proportion. All right. There's something, did we talk in here? We talked a little bit about why ants can't get super big.
No, you said we were going to
about that.
We talked about it.
You said you were going to tell us why,
Yeah, we did.
No, we didn't, did
why
we?
the legs wouldn't carry themselves using us.
We did talk about that?
Yeah,
You
we
didn't
did.
tell us why.
Oh, okay. Yeah, well, this relates to that. Okay, if when you're watching science fiction movies and they get these enormous, like King Kong could never have worked. King Kong, that ape couldn't have stood up. It would have broken its own legs and tried to stand up. Those ants that they show in these, the enormous ants or enormous beetles or spiders or whatever, no chance. There's no chance that could ever work. Because if you look at the physics of scaling things up, what we know is that the strength, the supporting strength of something, like a leg, let's say, is proportional to its cross-sectional area. So if you cut through the bones in a person's leg, if you cut through and you look at the cross-sectional area, legs are the size that they are on people for a reason, because they've evolved to be that way, because that's how much strength is needed for us to do the things that we've needed to do in our past, to hunt animals and do, we have to be athletic, we have to be able to do things like that, so they need to be a certain strength to support our weight to do those things. If they had been any smaller, TJ, then they would have broken. If they were any bigger, they'd be too heavy. They'd be unnecessarily strong. They'd be way too heavy, and we couldn't move fast enough. And it would take too much energy to build them. So they're just the right size. Same thing for insects. Insects have really small legs because they're so lightweight. They don't need these enormous legs in proportion to their bodies. If you look at an ant, their legs look really skinny. Okay, but if you were to scale them up, their legs would only, the strength of their legs, if I scale something up, let's say we take an ant or a person and we scale them up by a factor of 10. That means that the cross-sectional, the diameter of their legs is going to increase by a factor of 10, right? Because we can measure that with a measuring tape. Okay, that means that the areas are going to increase by a factor of 10 squared, which is 100. That seems like a pretty good deal. If I scale up an animal by a factor of 10, the strength of its legs goes up by a factor of 100. My goodness. So they ought to be able to support their own weight. But what about the volume? Now, volume is what we might call a cubic measurement. The volumes, take a square, for example. A square, the area of a square is just x squared, but the volume of a square is x cubed, right? So if I square if I increase the size of a three-dimensional object by a factor of 10, its volume is going to increase by a factor of 10 cubed. That's 1,000. Now, which of these measurements is going to be related to the weight of the object? Its height, its cross-sectional area, or its volume? Volume. Volume tells us the amount of stuff, right? The amount of tissue in an animal, total. So the weight, if I scale up an animal by a factor of 10, its weight is going to go up by a factor of its volume, 10 cubed. That's 1,000. Its weight increases by 1,000. Its supporting strength only goes up as its area does by a factor of 100. And so you see the gap there? If the weight's increasing by 1,000, but the strength is only increasing by 100, there's going to come a point where the strength isn't there anymore, right? And all of a sudden the creature's just going to break its own legs trying to stand up. If you look at dinosaurs, for example, if you look back at the, everyone's seen pictures of dinosaurs, and we know what they look like based on their fossils. Dinosaurs, what came to that? Oh my goodness, what am I doing? That would have been a disaster. If we look at dinosaurs, don't they always have this basic shape? Like if I'm going to draw it, and don't laugh at my drawing, but if I'm going to draw a T-Rex, doesn't it kind of look like there's the leg, and then the body just kind of looks like, right, there's my,
Pretty good.
right, there's my dinosaur. Right, here's its little, they look like birds, kind of, right? Birds are the closest living relatives to dinosaurs. So there's my T-Rex, and the legs are a little too long, but you get the idea. The body is relative to the size of the body. The legs should even probably be bigger than that. They probably should look more about that size. The legs are huge, right? If you look at those dinosaurs, their legs are enormous proportionally, much bigger than people's are, right? And why is that? Because they weighed so much. Because they were scaled up animals, and so as their weight went up, they had to have much bigger cross-sections of their legs to support that big weight. The bigger an animal is, the more it has to devote to this structural support. Okay? So that's really what we just talked about. All right.